Welcome back, everyone. In this video, we'll be continuing the section on the fundamental theorem of calculus. Now, in the last video, we only really looked at one problem and the theorem, the fundamental theorem of calculus, part 2, but we really noticed a lot of things about it, and we want to use what we noticed to help us going forward when we evaluate definite integrals. So we don't want to use a plus c because it's not necessary. We want to do just the antiderivative of each part. We don't have to go through and break it down into each individual possible step, unless if you're really only comfortable with that at this point. But what we're going to see in the rest of the problems is just basically we don't want to break any rules. We don't want to make any rules for integration or antiderivatives. We just want to make sure that we're doing everything the correct way. So number 2 here says evaluate the integral from 1 to 9 of 3 plus x squared over x. Now technically, compared to the one we did before, this was a polynomial which is continuous everywhere. This is not continuous everywhere, so technically there is a possibility you cannot evaluate this integral. And it's not something that we often check because we just kind of do it. But what this says is that this function inside here, the denominator 0 when x is 0. So this is not continuous. The function inside, 3 plus x squared over x, at x equals 0. It's fine everywhere else because any other x value is not going to make us division by 0. But luckily for us, the bounds from 1 to 9 don't have 0 inside, so we can do this. So since 0 is not between 1 and 9, we can do this. We can compute this. Now at this point, there are some examples when you have discontinuities that you can still integrate, but that's many sections in the future. So at this point, if we did have something like this, we would just have to say we cannot do it or D and E just because we don't have a technique. So really what I'm pointing out here is that you should always be able to do the integrals without really worrying about continuity at this point. But I like to go ahead and just introduce the idea because when it does come up and you have to start worrying about it, you don't want it to be a completely new thing. All right. So one thing I also need to go ahead and mention is that this is a division. We do not have a quotient rule for antiderivatives. So we have to use properties and algebraic simplifications. Now, one thing I'll remind you is we did do an antiderivative something like this before, and the point was to split it up. So we want to go ahead and do that. So once again, there's no rule for division for antiderivatives, which means we have to split it up. Now, what do I mean by split it up? Well, I'm going to first just start by rewriting it so I can write it in line like this. We split it up by doing the same thing we did in the previous sections. We can't do the antiderivative of the whole thing, but we can write each part over x, basically break up the fraction. And now you can simplify each part. Now, one thing I'll say is that for the first part, you have 3 over x. In a lot of ways, it's kind of simplified. But when we did derivatives and for the same thing for integrals, I prefer not having x's in the bottom and bringing them up to the top, even if it makes negative exponents. So the first part, we have 3 over x is 3, and 1 over x is x to the negative 1. So I bring that up to the top. I just make the exponent negative. Now for the other one, we just need to simplify. This is x squared over x to the 1, so we can completely get rid of the x on the bottom as long as we take 1 away from the top. So we just have x to the 1, or you can write just x because that's really what it is in the second part. Okay, so we're right there. We have 3x to the negative 1 plus x. Well, as we mentioned in the previous, every time we have a plus or a minus and some numbers, we can worry about just doing the integral or the antiderivative of the x part. All right, so when we do this antiderivative, you can go through and break it apart, but I'm just going to fast forward it because we want to get good at these. We want to make sure we're doing integrals efficiently. As we add more and more applications in for integrals and rules, if you're doing every single step out every single time, it's going to take a very long time and it's more spots to make a mistake. So try to go through the steps in your head. Well, if we broke this up, we would do the derivative of this or the antiderivative of this part plus the antiderivative of this part, and the 3 wouldn't matter. So really we want to answer 2 questions. What is the antiderivative of x to the negative 1? And what is the antiderivative of x? And I'll use this in different colors just to really highlight them. Right. Now the 3 is just going to stick around. We're going to figure out what the antiderivative of x to the negative 1 is. So I'm going to keep this kind of highlighted. The antiderivative of x to the negative 1 is going here. And because we have a plus between, I'm going to have a plus. And then the next thing, we want to do the antiderivative of x. So what's going to go here is the antiderivative of x. And if it's a little shaky just the way I'm drawing it out now, just keep in mind, maybe when I actually write down the answer, it'll make a lot more sense. All right, well, the antiderivative of x to the negative 1, that's not the power rule. This negative 1 power is the only power where it's not using the power rule. That is the special natural log rule. This is the natural log of the absolute value of x. And we stressed back when we introduced this that the absolute value is important. So just make sure you include it. Now, technically, you can go through and understand that because we only care about x from 1 to 9, it's already positive and you don't need the absolute values. But there's nothing wrong with keeping them on. And if you leave them off, you have the possibility of actually messing up. So you want to make sure, just keep them on. All right, and then the antiderivative of x is x squared over 2. Add 1 to the power and divide by the new power. Let me write it more clearly so we don't have any issues. And because we're doing a definite integral, I'm not writing the plus c. The way I like to think about definite integrals is this evaluation bar from 1 to 9 replaces the plus c. That's the way I like to think about it. If I have numbers here, I'm going to do this. If I don't have numbers here, I don't have anything to write in, so I need to write a plus c at the end. All right, now just to quickly review, in case you were a little shaky, maybe this makes sense now. The numbers just stick around, so 3 just sticks around. The pluses and minuses just stick around, and then we do the antiderivative of each part. So the antiderivative of x to the negative 1 was this. The antiderivative of x was this. And hopefully you are comfortable with that. If not, go through the steps of the previous problem. Maybe pause the video, go through the steps of the previous problem, break it up over the pluses and minuses, which we only have 1 of. Then factor out the 3 of the first one, and you should be able to arrive to this conclusion. Now, as far as simplifying before we plug in, there's really nothing to simplify. We have x squared over 2, nothing to cancel in the fraction there, and this is just 3 times the natural log of x, absolute value, so nothing to cancel there. So I'm going to kind of do what I did last time. I'm going to have a parentheses minus and another parentheses, and in the first one, this is when I plug in the top number. Plug in x equals 9, and this is when I plug in the bottom number, plug in x equals 1. Right, so let's go ahead and do that. If we plug in x equals 9, we get 3 times the natural log of the absolute value of 9 plus 9 squared over 2. And then when I plug in x equals 1, I get 3 times the natural log of the absolute value of 1 plus 1 squared over 2. Right. Now, because we already have positive numbers in here, when we do the absolute value, it does nothing. But one thing you do want to remember is the natural log of 1 is 0. So this is actually 0. And in the front here, the parentheses isn't mattering, and the natural log is going to make it so that we can't combine these at all. So this is 3 times the natural log of 9 plus, and then 9 squared is 81 over 2. And then what are we subtracting off? Well, we're actually only subtracting off 1 squared over 2, or 1/2. So we can get rid of the parentheses there, just distribute it or put it to the 1/2 because this is 0. And actually we can finish up here because all we have to do to simplify 81 over 2 minus 1 over 2 is 80 over 2. I already have a common denominator. And it's positive because this one's the plus and this one's the minus. We have 80 over 2 and 80 over 2. Weird way to write an 8. Let me go ahead and just completely fix that. But 80 over 2 is 40. So we can go ahead and just finish up as 40. 3 times the natural log of 9 plus 40. Now this is a good answer. Sometimes you can see a different answer here. If you type this into maybe Wolfram Alpha and you wanted to know the answer, you might not see 3 times the natural log of 9 because they might use the log rule that says you can take the 3 and move it up to the exponent and get the natural log of 9 cubed plus 40. And 9 cubed is 729. So this is the natural log of 729 plus 40. Now you don't have to do that. So you can stop right here. And there's nothing wrong with that. I wouldn't stop before here. So because you definitely want to simplify the 80 over 2 to 40. But either one of these is good. I just wanted to make you aware that if you type in something like this, even if you get it right, you might, just check your calculators or something and see that this is the correct answer. I just wanted you to know where it came from. Right? Right. So pretty much, the two things you really have to look out for at this point is we don't have rules for multiplication and division inside of an integral because we don't know how to do antiderivatives with multiplication and division. So you just need to go through and algebraically simplify. If it's multiplication, think about foiling. If it's division, split it up like this. All right, now number 3 here says evaluate the integral from pi over 4 to pi over 3 of secant of t times tangent of t. Now this is another one of those things where you'd have to be careful about the continuity part and pretty much emphasize that at this point we don't know how to integrate if it's not continuous. So you should be continuous on your integral from pi over 4 to pi over 3. But all the trig functions besides sine and cosine have points of discontinuity. Luckily for us, secant of t times tangent of t is continuous on the interval pi over 4 to pi over 3. If you want some clarity why, actually all the trig functions are continuous in the first quadrant, and these are all angles in the first quadrant. So if you remember way back to the beginning of trig and talking about that stuff with the quadrants, all the trig functions are continuous in quadrant 1. So if you take any combination of them, it'll be continuous as long as your bounds here are in quadrant 1. Right. One thing to point out is that we're using t here. So t equals pi over 2. This is actually not continuous. And you can type it in your calculator. What is secant of t or secant of pi over 2 times tangent of pi over 2? You will get an error because it's not continuous. So what that means is if an interval that we wanted to integrate on, so let's say it was not pi over 4 to pi over 3, but pi over 4 to pi over 2, we would not be able to integral. So if an integral contained pi over 2, then this could not be done. At least the only way we know how to do integrals. Right, but the nice thing is when it comes to antiderivatives, the trig antiderivatives are always kind of weird. I'm going to rewrite it just so I can write it in line. But if you look back at your formula sheet, you actually have the exact formula for this antiderivative. Because the derivative, the derivative of secant of t is this. That means the antiderivative of secant of t times tangent of t is actually just secant of t. Let me go ahead and just write that in a comment because it feels like it goes so fast. But the antiderivative of secant of t times tangent of t is just secant of t. Right, and once again, you should have that little sheet with all the formulas and you should be able to see that. But you can also know that from the forward direction, the derivative of secant of t is secant of t times tangent of t. Okay, so that's all we have to do for the antiderivative part. We still have to make sure we finish it up. We don't write the plus c because we do our evaluation bar, pi over 4 on the bottom, pi over 3 on the top. And we do want to go ahead and plug them in. So we got secant of pi over 3 minus secant of pi over 4. Now, I guess one thing we didn't really mention here, but it doesn't matter if the top and bottom number is bigger. If you really hate the top bottom or the top number being smaller than the bottom number, which here it's bigger, so it's fine. But if you had like 1 on the bottom and 0 on the top, you can still do this. You just have, you plug in the top number minus plug in the bottom number. So no issues there. But if you're like me, don't probably know the exact values of secant, but you should, or be able to deduce the exact values of cosine. So secant is 1 over cosine. We have 1 over cosine of pi over 3 minus 1 over cosine of pi over 4. And now cosine of pi over 3 is 1/2. So that's the bigger angle in quadrant 1. Minus, and then cosine of pi over 4 is the square root of 2 over 2. And when we have a fraction, something over 1, you just bring it to the top and flip it. When the top is 1, it's just going to be this flipped. So this is going to be 2 minus, and then flipping this, it's 2 over the square root of 2. Now you can just stop there. You don't need to rationalize as far as when it comes to just numbers. So the square root of 2 being on the bottom is fine. And this is our answer. Okay. Once again, when it comes to the trig functions, if you have something weird with trig functions inside here, so one other thing that could look weird is like a secant squared. It's because the antiderivative of secant squared, there's actually directly a formula for it, and it's tangent. So keep that in mind if you have stuff that looks kind of weird here, especially if it's like multiplication, because we just talked about how we cannot integrate with multiplications, then there must be a formula. So keep that in mind, especially when you see the trig stuff. Right. And now the last one here, this one is really more along the lines of just remembering that when you're doing a definite integral, you're finding something like an area. I just want to reiterate that point again. So it says graph the function below. You don't have to do this by hand. You can use it in the calculator just to visualize it. And then use this setup to set up a definite integral to find the area that lies between it and the x-axis. Then evaluate the integral. Well, we want to graph y equals cosine of x from negative pi over 2 to pi over 2. So let's go ahead and do that. And once again, you should know this general shape. You should be able to really do this by hand, but we want to use technology in a smart way, and graphing is probably the best feature as far as technology goes when it comes to math. We don't want to actually do these things by hand if we don't have to. So the x-axis, I'm going to do pi over 2, or sorry, negative pi over 2 to pi over 2. I don't care what happens after that. Step size, I'll just do pi over 4 so we can see kind of nice intervals. And we know the graph of cosine is always stuck between negative 1 and 1. And don't worry about the step size there. But the point here is that I'll scroll a little bit just so we can see at pi over 2, or from negative pi over 2 to pi over 2. So this part of the graph of cosine, it's all above the x-axis, which means when we do the integral, it's going to give us the exact area. If it was all below the x-axis, then we would have to do a negative of the integral. But because it's above, we can just do the integral itself. So let's just keep that in mind. We're going to integrate cosine of x from negative pi over 2 to pi over 2. And that's going to give us the exact area because our curve is above the x-axis the whole way. All right, so that's the setup part. I'll just kind of write what I wrote here just because cosine of x is above the x-axis on the entire interval from negative pi over 2 to pi over 2. I always write above, but it can touch as well, which it does at the endpoints. The integral, the definite integral, will give us the area. All right, so that means to figure out this exact area, we just integrate from the smaller number, negative pi over 2, to the larger number, pi over 2, of cosine of x. And don't forget your dx. So you have to make sure you do that. Well, what's the antiderivative of cosine of x? That's actually just sine of x. So it's sort of like the last one in that we already have a direct formula for it. We don't have to do anything extra. We definitely need our evaluation bar, the negative pi over 2 to pi over 2. And we go ahead and plug it in, and we plug in the top number. So we get sine of pi over 2 minus, and then plug in the bottom number, sine of negative pi over 2. Sine of pi over 2 is 1, and sine of negative pi over 2 is actually negative 1. And 1 minus negative 1, when you add them together, gives us 2. So in fact, the area of this is 2. It's exactly 2, which I always find kind of weird because it's such a weird shape. What are the odds this thing has area exactly 2? Apparently it does. There's nothing weird. There's no weird radicals. It's just exactly 2. So very cool. But going forward, doing problems like this where we set up integrals and not just giving them ourselves, that's something we have to start doing a little bit because we're going to want to do applications of integrals. And they're really the big part of doing applications of integrals. It's not going to be evaluating the integral. Yes, that can be challenging. It's really going to be, can you set it up first? But we'll have tons more practice of evaluating integrals before we get there, and I'll see you in the next video.